So in this module, we're going to talk about software design and coding and the various aspects of that. Again, this covers chapters 7 and 8 respectively. Okay, so like we saw in the previous module, we talked about software requirements and we broke these software requirements down into high-level requirements that are really developed from analyzing the system requirements and safety-related requirements and system architecture, and low-level requirements that really are developed from the high-level requirements to kind of add extra detail. And these are really developed to a level from which you can directly, such that you can directly derive the source code from these requirements. So basically, in design, we're deriving these low-level requirements and the software architecture. And then taking these low-level requirements, we actually generate source code. Then we take the source code, modules, and all these modules integrated to find the executable code that we can then test and verify. Okay, so the design description, the design output is really the low-level requirements plus the software architecture, plus of course all the derived requirements. And remember, derived requirements are requirements at the design level that cannot directly be traced to high-level requirements. So this document should include algorithms, input-output definitions, detailed data and control flow, as we specify specifically in the software architecture. Things like resource management, scheduling, and a variety of other things that you show here. But you have to make sure that all these low-level requirements can be traced back, of course, to high-level requirements. Again, also the software architecture, it really kind of shows you all the major software components and subsystems, but also tell them how they're interconnected. It more or less kind of represents the control flow, in other words, things like the call tree, in what order you're going to be calling all the subroutines, and what modules are called within what other modules. And of course the data flow, how moves data between the various modules. So I gave a very simple software architecture diagram here with two components here, and this component takes pseudo ranges in time and outputs latitude, longitude, height. So this component could be a position calculation component. Then inside this component we could specify the functionality by having a set of low-level requirements that actually are being used to turn the pseudo ranges from GPS, for example, into a latitude, longitude, height calculation. Then this latitude, longitude, height will be used in component Y to find a terrain height based on a terrain database. And then you're going to check out if this terrain is larger than 200 feet. So this is kind of a ground proximity warning, a little example. Now remember, the low-level requirements is what you're going to be coding. Okay, so if you look at the low-level requirements, they're really design details. High-level requirements are way more exact, closer to the system. Low-level requirements really need to have so much detail that you can derive the code from it. Yeah. Of course, they must be uniquely identified, but that's the same thing with high-level requirements. And they must have kind of all the attributes from chapters 2 and 6, so all the attributes of good requirements that we talked about before when we talked about high-level requirements or system requirements. One difference though with high-level requirements and system requirements is that there's way more focus on how exactly you're going to implement a particular functionality rather than what needs to be implemented. Of course, again, like I said before, you must be able to come up with a test case for each one of these low-level requirements, so they must be verifiable. Now, in some cases, examples, you may not need low-level requirements at all. The high-level requirements are good enough or give you enough detail so that you don't need to use a hierarchy. What you find out typically that for critical software, they tend to have way more detailed low-level requirements because it's way more important that you tie down the things that you want to express in the source code. So usually, of course, these are textual, but there will also be some, some of these are represented by models, and we're going to be talking about more of this in module 12. Now, the alternative way of looking at this, and you see sometimes, is that the low-level requirements look kind of like pseudocode or even things like MATLAB code. In other words, you have a set of code. Well, this is allowable, but what you have to worry about some of the concerns associated with using pseudocode as the low-level requirements. Yeah. A couple of them are stated here, and these can be found in the textbook with some extra material. One thing is that if you use pseudocode for the low-level requirements, then that may result in a really large granularity jump. You know, for example, if the high-level requirements are very much textual and you immediately go from this very textual requirements to pseudocode, there may be too much of a jump in abstraction between the high-level requirements and low-level requirements. Also, they may take away from architectural detail. Yeah. So, in other words, they may, by using those, data coupling, control coupling issues may not necessarily be as obvious. Also, one thing to realize is that if you have something like this, it may be much tougher in some cases, not in this one, but in a lot of cases, to uniquely identify the low-level requirements within the pseudocode. This is a very small piece of pseudocode, but if the code's a little bit longer, it's hard to say, is this really one requirement or is this multiple requirements? Well, so if it's hard to uniquely identify it, it's also going to be much harder to bidirectionally trace it to high-level requirements. And finally, one of the concerns here is that if you want to perform structural coverage analysis using low-level testing, it's typically kind of if you perform structural coverage using low-level testing, that's kind of typically inadequate since the code and pseudocode are so similar. Okay, so for design approaches, breaking basically in structural design, where it's basically approaches in which you have the clear data flow, and examples with data flow diagrams, control flow diagrams, decision tables, state transition diagrams, call trees, call graphs, flow charts, or just plain textual descriptions. This component shall add numbers A1, A2, A3, A4, and divide the result by 5. Something very simple, similar like that. It's structurally defined. Of course, there's also object-oriented design techniques that you can use. In order, a couple examples, you can use UML, swim lane diagrams, state charts. So there's a variety of other things. And of course, one thing that you see here is that with ee6083, there is now another supplement that really focuses on just object-oriented techniques, and this one is actually given and is talked about in a later module. So a couple examples here for structure design examples: transition diagrams, truth tables, flow charts, structure charts. So these are all provide you with some form of logic flow or data flow or control flow. Whereas if you look at object-oriented design, you're really thinking in terms of classes and objects that interact. So tools would be really more like UML tools, UML diagrams, sequence diagrams, activity diagrams, in order to tools that you typically have when you perform object-oriented design. Now, the Rieger's book on software requirements is actually a good book if you want to look at some of these design issues. And on Blackboard, I added 2 articles by Rieger's that are kind of related to what's in this textbook as well. So what's characteristics of good design? Make sure it's kind of abstract, it's modular. Of course, we saw this before, we want to have very strong cohesion and loose coupling. We don't want to have loose cohesion and strong coupling. We want to have strong cohesion. In other words, all the tasks, all the activities within one module should be related to one particular task. And loose coupling, we don't want to have too much coupling between the different modules. We try to limit that as much as we possibly can. Want to hide information as much as we can. Keep it within a module. Don't have huge structures that you pass on with a whole lot of information. Or, for example, use global variables. Not a good idea. when you want to make sure that you reduce complexity as much as you can. And if you can come up with something that you can repeatedly use, that will be really a good idea. Of course, a good design must be easily maintainable, robust. You want to do a lot of robustness checks even in your low-level requirements definition. Make sure to document the design decisions, safety features, make sure it's reviewed and tested. Yeah. Try to come up and avoid some of the undesired features really, which is recursion, self-modifying code, and dynamic memory allocation. Of course, these are very tempting when you have a computer science background and you try to implement some very effective algorithms, but for a lot of safety critical applications, these have like a variety of side effects that you don't want to deal with. Again, I had talked about this before. Just repeat the slide so you have it given here as well, but I talked about this in the previous module. In terms of testability, make sure that it's operability. Make sure the software does what it's supposed to do as per the requirements. Observability you need to access. All the inputs, the internal variables, and the outputs can be observed during the execution. That's the only way you can actually look at them, test them, and check out if the tests actually passed or failed. Make sure that you can control the outputs by changing the inputs. This is something that we'll get back to a little bit when we talk about the module on verification, module 8 and 9. Make sure that you can break down the code in components. Yeah? So these components can then be taken and tested independently. Yeah? So you want to take, if you have the software and it consists of a variety of components, we can take the components out of the bigger picture and test it independently. Then combine the components together and perform integration testing. Simplicity, if you have a software as a simple functionality, you also make sure that the structure is pretty simple and that the code's pretty simple. It's pretty straightforward to look through the code as well. This makes it also easier to, for example, code walkthroughs, and of course for design especially, to do design reviews. Stability is always a good thing. Make sure that the software is not changing, slightly changing. Good documentation. Okay, so if you look at the verifications of the design process, again, the low-level requirements must be compliant with the high-level requirements, means in technical agreement. It must also be traceable, and of course the same thing, the software architecture must be compatible with the high-level requirements.